This problem requires you to simplify radicals with variables. Alright, so you're going to deal with the 12 like you know how. You're just going to look for something that goes into 12 that is on this perfect square list. But when you look at x squared, you have to realize that the square root of x squared is just x. The square root of x to the fourth is x squared, and so forth. You kind of see the pattern. It's just half of what's underneath there. The reason being, you always remember, if you try out with a real number, the square root of 5 squared, this is the opposite of each other. So squaring something is the opposite of square rooting something. So they almost like cancel each other out. If you think about what that number is underneath there, that's the square root of 25, which is just 5. Okay, in the same token, you guys also know that radical 5 times radical 5 is also just 5. So there again, those are opposites. Alright, so if I square a square root, it undoes it, or if I square root a square, it undoes itself. So since they're opposite operations, they undo each other. So with that explanation, we can kind of try to tackle this one here. So the 12, I know that 4 goes into 12, so I make that 4 times 3. And I already know that x squared is already a perfect square. So when I rewrite this as square root of 4, square root of 3, square root of x squared. That becomes a 2, that becomes x. So 2x, this is not a perfect square, so it's going to stay underneath. And there you go. So number 2, I look at the 60. I'm going to break that up into 4 goes in there 15 times. So I double check my list here, make sure nothing else on this list goes into 60. I know 4 does. Check all the other ones, none of them do. So that is my greatest perfect square. Now I'm going to break the x cubed into x squared times x, because I know that that's a perfect square. So x squared times x gives me x cubed. And then y to the fourth, again, it's a perfect square. Y to the fourth, the square root of that, you just get y squared. So instead of having to write all this back out again like I did up here, it's just kind of easier to say, okay, which ones are my perfect squares? This one, and this one. So those are all going to end up out front. They're gone. Okay? So rewrite those and then cross them out. Oops. So the square root of 4 is 2. The square root of x squared is x. And the square root of y to the fourth is y squared. So all three of those went out front. What's left? The 15 and the x. And we are finished. Look at example 3. We have a coefficient out front. That's no big deal. It's just going to kind of come along for the ride. And the perfect square that goes into 72 is 36. 36 times 2. And then again, I know n to the fourth is a perfect square. Yeah. N to the fourth times, I forgot to do it. I'll just put it on the end there. So which ones are my perfect square? The 36, the 4, the m to the fourth, the m to the second, the n is kind of off by itself. So all three of those are going to join the 4. So I have 4 times square root of 36 is 6, square root of 4, n to the fourth is n squared, square root of m squared is just m. What's left? The 2 and the n. And then I just kind of put this all together. That's 24 n squared m square root 2n. All right, last one. Again, the -5 is just going to stay out front. It's waiting for something to join it. So I break this into 144 times 2. I know the square root of 144 is 12, so that works out kind of nice. K is kind of by itself. J to the third, I'm going to break that up into j squared times j. And then I know all even powers of variables are going to be perfect squares. So I have 1, 2, 3 perfect squares that are going to join the -5. So here we go. -5 times square root of 144 is 12. Square root of j squared is just j. And the square root of m to the 8th is just m to the 4th. Those all went out front. What's left? A 2, a k, and a j. So just collect those or put them together. And we're done.